All right, I'm going to go ahead and work through this question. This is question 3 from the 2017 administration of paper 2. So it's actually paper 23. It's paper 23 from May, June 2017, question 3. It says define electric field strength. You want to say that the electric field strength is the force per unit positive charge. Force per charge, but if we define it as the force per unit positive charge, we capture the vector nature of this, right? Electric field points in a direction, the direction that the force on the positive charge goes. So force per unit positive charge is a good definition of electric field strength. Question goes on to read, an electron is accelerated from point A here to point B by a uniform electric field, as illustrated in figure 3.1. The distance between A and B is 12 millimeters. So we'll call that a displacement S, 12 millimeters. The velocity of the electron at A is 2.5 kilometers per second, and at B, 18 megameters per second. Okay, so we're going from the initial speed here, U equals 2.5 kilometers per second to a final velocity V of 18 megameters per second. And you see, you want to get in the habit of, okay, milli is 10 to the negative 3, kilo is 10 to the positive 3, mega is 10 to the positive 6. And you can just convert those metric prefixes just like that, kind of spell out sort of what we got here, and avoid any mistake of like forgetting the units. You can see that within this question, they're assessing the student's knowledge of their metric prefixes, right? They've included everything with sort of a different metric prefix, and you have to have them all in the same SI units. So that is a necessary step, and I kind of like to take care of it up front. All right, we'll bring all those values down here. There they go. Not that far. Trying to calculate the acceleration of the electron. And if we know that the displacement is 12 millimeters, the initial and final velocities sort of are given here, then perhaps the easiest path to the solution is v squared equals u squared plus 2as, because we're solving for the acceleration and we're given the displacement and the initial and final velocity. We're not told how much time it's going to take for the electron to travel from A to B, but we could calculate that if we really wanted to. We could do something like the known displacement equals 1/2 the known initial and final velocities times time. So here the only unknown would be time. We could calculate that, and once we knew time, you know, it's fair game. Any equation will work at that point. You know how much time it took to get there. We could calculate the acceleration just as, you know, v minus u over that time t, right? But we have to know the time first. So using this equation at first, just saying, oh, I want to know acceleration. Here's the sort of most basic equation for that, right? The definition of acceleration, rate of change of velocity. But you find that both the acceleration and the time are unknown, so you have to sort of go through your equation and say, well, I can use this one to find the time if I really wanted to use this equation. But this equation does not contain time. The question doesn't ask us for time, so we just sort of plug in everything this way. So plug in that value for B, plug in this value for U, plug in that value for S, solve for A. Okay. So A would be B squared minus B squared over 2S, or 18 megameters per second squared minus 2.5 kilo per second. That one squared over twice the displacement. Let's find some numbers here. 18 and 6. 2.5, 5, 10. All right, anybody already calculate that? What did you get?
I got 7.49.
Anybody else solve it? And I mean, any one of us could be right. We all got different answers, I think. Did you all agree?
No.
What did you say? That's even different than what I got. I'm going to double check my calculations here. 18 times 10 to the 6 squared minus 2,500 squared equals 5/2 by 12 and -3. Yeah, I got the same answer that I got a moment ago. So I'm either making the same mistake again and again, or this is the right answer. So you got the same thing? What did you get? 10 to the 12. 2,500. Anybody else calculate this out here? I'd like to have some consensus. I'd like somebody to say, I get this answer, and I go, oh, all right, and that's the thing that's in my calculator. Who's got it? Who's got it?
1.35.
That's what I get. 1.35 by 10 to the 16. So that's like, that's what I was going to say. I had that all along. Why didn't you say it? It's an acceleration, so it's like 10 to the 8 meters per second for velocity. You know, think of that as the speed of light. That's what good for accelerating that much. Question goes on to read, what's the calculate the change in the kinetic energy of the electron? What's the change in the kinetic energy of the electron? So probably different ways that we could approach this. The change in kinetic energy, so the general way to think about it is kinetic energy final minus kinetic energy initial, right? That would give us the change. The final kinetic energy is going to be 1/2. The mass of an electron is 9.11 by 10 to the -31 kilograms. Well, that's its rest mass. It's not really at rest. Anyway, that's a factor out anyway. And then the final velocity was the 18 megameters per second. All right, so 1/2 mv squared, that would be the final kinetic energy, minus the initial kinetic energy would have been 1/2 the same mass, 9.11 by 31 kilos, times 2.5 by 10 to the 3. So that's one way to solve it. The other way is like knowing that the acceleration was 1.35 by 10 to the 16. we might be able to calculate the force on the electron, right? F equals ma. And then once we know the force, the change in kinetic energy is equal to the work done, work kinetic energy here. Okay, so the work is the change in kinetic energy. And work we know is the force times the displacement. So once we know sort of the force that was exerted on it to cause this acceleration, we know it was displaced over 12 millimeters. And so these two calculations should agree. Two different ways to sort of think about solving for the change in kinetic energy. Things only change their kinetic energy when work is done to them. The work is being done on the electron by the electric field force per charge, right? This electric field strength force per charge. So let's work on that together here. We've got about 10 minutes left. All right, I'm going to solve for the force up here first. So we've got the force would equal 9.11 by 10 to the negative 31 kilos times 16 squared. So keep that on my calculator at 1.35 times 1.35. So I get a force of 1.23 by 10 to the negative 14 newtons. If I just multiply that by 12 millimeters, that should be the change in kinetic energy using work kinetic energy theorem. Okay, so times 12 and to the negative 3, and I get a change here, kinetic energy, the work done, 1.5 by 10 to the negative 16 joules. Okay. I'll solve this. 18 times 10 raised to the 6 squared times 9.11 by 10 to the negative 31 times a half. So I get for this guy right here 1.47582 by 10 to the negative 16 minus 500 squared. So basically, the initial kinetic energy is like negligible compared to the final kinetic energy. It had an initial kinetic energy of 2.85 by 10 to the negative 24. So we say like, why is this so negligible compared to that? If I were to subtract this away from it, like, let me actually do that on my calculator. So I'll make that negative, I'll add it back to the 1.47582 by 10 to the negative 16. And like this number changes 1.4758199. Okay, so I mean this is way out. Like, 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 11, 12, 13, 14, 15, 1, 4, 7. Like that's that number. I'm subtracting away from it. That. So kind of like, well, that little bit of initial kinetic energy doesn't really do anything. So you can see how this is my answer up here, 1.5 up to -16 like that. That's negligible. You should get 1.5 by 10 to the negative 16. Either way you calculate it. Couple of minutes left. Plenty of time to calculate the electric field strength. The electric field strength is simply the force per charge. And the force, remember we calculated from the mass times the acceleration. Right? I forget what it was. It was like 10 to the negative 14, something like that. So we have 1.23 times 10 to the negative 14 newtons over the charge on an electron, 1.6 by 10 to the negative 19. Right, so elementary charge. 1.23 by 10 to the negative 14 divided by elementary charge 1.6 by 10 to the negative 19 equals 76,875 newtons per coulomb or volts per meter. And so we can call that 7.7 by 10 to the 4. An alpha particle moves from A to B in the electric field. We haven't studied alpha particles yet, so don't worry about it too much. But I will just tell you that an alpha particle has 2 positive charges in it, and it's a helium nucleus. So compared to an electron, the differences are that one, it's positively charged, one negative, and it has twice the charge, right? So if this is force per charge, and this thing is twice as charged, it's going to experience sort of twice the force. Okay, it's the force per unit charge. And so even though an alpha particle is more massive, more inert, it's still going to be accelerated more because it's going to have twice the force on it in that uniform electric